So let's take a look at problem 1.64. In this problem here, they tell us that we have a spherical container. It's made of stainless steel, and it's going to be used for storing reacting chemicals that provide a uniform, so we know it's a uniform, heat flux to its inner surface. Now this canister is then going to be submitted into a liquid bath where the temperature of T infinity is going to be less than our T sub I, where our T sub I is the initial temperature of the canister wall. So then we can come down here to our given diagram. We can see, okay, there's our canister right there. Inside is our reacting chemicals right here. We can see the temperature right here that they told us this initial temperature of the canister wall is given to us is at T sub I, and this is equal to 500 K. We can see we have our rho value here of 8,055 kilograms per meter cubed. We have our specific heat here of 510 joules per kilogram times Kelvin. And then up top here, we can see we have this radius right there of 0.6 meters. So that's our outer radius. You can see it goes from the center here all the way to the outer surface of the canister right there. Our inner radius is given to us 0.5. So from that, we can tell the thickness of the wall. And our surrounding area here, we have our bath that's submerged in with a temperature of 300 K. So there's our T infinity right here, and T infinity is less than, that 300 K is less than our T sub I. And our H value here is given to us as 500 watts per meter squared times Kelvin. Now there's two separate things they want us to solve for. We have a part A and a part B. And in part A, they also give us this assumption. They want us to assume negligible temperature gradients in the canister wall and a constant heat flux. Now with that information, they want us to develop an equation that governs the variation of the wall temperature with time. So variation of temperature with time during the transient process. Also, they want us to find the initial rate of change of the wall temperature if we have our heat flux right here given to us as 10 to the 5th watts per meter squared. And then for part B, they want us to find the steady state temperature of the wall. So now that we've had that chance to read through the problem statement and take a look at that diagram, the next thing we want to do is create our setup page for our solution here. So on the setup page, recall we want to draw a simplified version of the diagram, which we can see up here. And we also want to write out everything that they give us in the problem, the variable name, the value, the units, and how it physically relates to our problem. Also, we're going to write any assumptions we're going to make and write down clearly what they're asking us to solve for. So we do that here. We draw out our diagram over here on the right. We can see, okay, we have our stored energy in there. We have our inner radius. We have our outer radius given to us. We have temperature of the surroundings. We have over here, this is going to be stainless steel, and this is going to be a T sub I given to us as 500 K, and this is the initial temperature of the wall, the canister wall. And we can see we have some convection going on here as well. So with this diagram here and looking back at our problem statement and initial given figure, we write out all our givens. So we know that our inner radius, R sub I, is equal to 0.5 meters. Our outer radius, R sub O, is equal to 0.6 in units of meters again. Our T sub I, or our canister temperature in our wall, is 500 K. Temperature of the bath surrounding is 300 K. Our H value, our heat transfer coefficient, is equal to 500, and we have units of watts per meter squared times Kelvin. Our density value is given to us here. Our rho is equal to 8,055 in units of kilograms per meter cubed. So you can see this is important that we write out our units. We want to double check that everything's in the correct units. Do we need to do any conversions? And this is going to help us with our unit analysis to make sure we've plugged in correctly to our governing equations. We also have our specific heat given to us as 535 in units of joules per kilogram times Kelvin, and we have our heat flux here is given to us as 10 to the 5th in watts per meter squared. So they gave us a couple assumptions within the problem statement. Negligible temperature gradients in the wall, constant properties, uniform time independent of heat flux at the inner surface, and then what they ask us to do is solve for a couple different things. So I come down here, write out my finds, what they're asking me to solve for. So there's a part A and a part B that we're going to solve in this problem right here. So our part A tells us the change, the rate of change in the wall temperature. There's a rate of change in the wall temperature, so we can see here, rate of change is change relative to time right here in our temperature, dt of our temperature right there. And they also ask us to find our, in part B, our steady state temperature. So now that we've had the opportunity to read through the problem statement and create that setup page, we need to go back to the setup page, look through all of that given information that we've now neatly organized and exactly what they're asking us to solve for. From there, we can begin our solution. And at the beginning part of our solution, what we always want to do is come up with a governing equation. And I like to start with a very general one and start plugging in from there. So we're going to start with our energy balance equation. We have this relationship right here, where we have over here our rate of energy transferred into the control volume. This is going to be based off of the heat flux that they give us. We have our rate of energy transferred out of our equation here. So we have a convection term over here that we're going to use for this. And then on the right-hand side, we have our rate of increase of energy stored within the control volume here. And now we can recall this relationship down here for the change in thermal energy with the relationship to time. So we have there's our E dot ST is equal to d over dt of rho, V for volume, specific heat times that temperature right there. So now we can take this information here and we can adapt it specifically for our problem. So as we adapt that governing equation to our specific problem here, we have this relationship shown here. And we can reference back to equation 1.12, the different versions of this within our textbook on pages 14 through 17. So we have our inflow, our outflow, and our stored term right here now, modified specifically for our problem here. Another thing that we want to recall when we're doing this here is we have that our heat rate is equal to our heat flux times our area. And we got to think of what is the surface area of a sphere. Well, we have this relationship for the surface area of a sphere is 4 pi r squared. We also want to take a look. Now we're going to need a volume term on the right-hand side of the equation. The volume of a spherical shell is given to us as V is equal to 4/3 pi times our r outer cubed minus our r inner cubed. And those are both things that they give us within the problem statement. So plugging in, we can say that our Q sub I right here, heat flux, is equal times our area here, which will come up back up to our area right here, which is 4 pi r inner radius right here squared, minus our A outer, which is 4 pi r outer squared, times our heat flux convection term right here, which we recall back for our equation for convection term is H times our temperature difference, T minus T infinity in this case here. And this is equal to our right-hand side of the equation here. Now we have our volume term times rho Cp ddt, where our rho is our density, Cp is our specific heat right there, times d over dt there. So we can plug in here from our volume term right here. We can see our volume plugs in like that there. We end up with this 4/3 pi times r not our outer squared minus our inner squared times our density times specific heat times that d over dt, where this is what we want to solve for. So the next step in this is to go through and solve for this dt over dt, or ddt of our temperature. So now the next step in our solution here is to solve for the change in temperature with respect to time, d over dt of our temperature term. We do that there, and then we can take a look at what we have on our left-hand side of the equation over here in this fraction. We take a look, and in the numerator we have 4 pi and a 4 pi that we can pull out in front, and we also have a 4 pi over here on the denominator that we can pull out in front there, and then we can see we have this 1/3 that we can bring up and flip up to our numerator there. So that's what we're going to do. We're going to pull out that 4 pi, and we're going to move our 1/3 up to the numerator from our denominator there. And when we do that, we can see there's our 3 up top there. When we flip that 1/3, our 4 pi on the numerator cancels with our 4 pi on the denominator, which does simplify this fraction down, this relationship down. We can see now we have 3 times, parentheses here, we have our heat flux term, which is given in the problem statement, times our inner radius squared, minus h times our outer radius squared, times our difference in temperature here, T minus T infinity there, all over our denominator now of our density, specific heat, and the difference between our outer radius and inner radius cubed right there is equal to our change in temperature with respect to time, ddt of our temperature T right there. So now that we've taken the time to simplify this down, cancel things out, and it's a little bit neater and easier to plug in, that's exactly what we're going to do, is we're going to plug in our known numeric values. So this is where it's great to have that first setup page. We can reference back to that setup page, look at exactly what the values are, what units there are, do our unit analysis. As you can see here, I've paid attention and kept track of all my units within this so I can do all my unit analysis and plug in order to solve for this change in temperature with respect to time right there. So we plug that in, our 3 is right there, we plug in here, well, this was given to us, that heat flux value right there is 10 to the 5th in units of watts per meter squared. We have our radius right here of 0.5 in units of meters squared right there. plug in our value for our H right here was given to us as 500 watts per meter squared times Kelvin, times our outer radius of 0.6 meters squared, times our temperature difference of 500 minus 300 units of Kelvin right there. Plug in our density term of 8,055 in units of kilograms per meter cubed, our specific heat over here, 535 joules per kilograms times Kelvin, times over here our outer radius cubed minus our inner radius cubed in units of meters squared. So we'd like a look, everything's Kelvin, Kelvin, meters, meters, kilograms, kilograms, everything checks out. And when we do our unit analysis cancel out, we find that our change in temperature with respect to time ends up being in Kelvin per second. So change in temperature is Kelvin, time, second, checks out, unit analysis works out. We end up with negative 0.84 Kelvin per second for that change in temperature with respect to time there. So that's great that we did our unit analysis out. It really does help us double check and make sure we plugged in everything correctly. So now that answered part A of our problem, which again is a great reason to have that setup page, because there may be multiple things you're solving for. You always want to go back and double check, have I finished the problem? The answer in this case, no, we haven't. They also want to find the temperature at a steady state conditions. For steady state conditions, our right-hand side of that energy balance equation right here, stored energy term, rate of stored energy term becomes 0 right there. So that right-hand side becomes 0. So now we just have our inflow and our outflow over here. So we can plug back into those again with our governing equation right here, where we have our heat flux times that area of the inner minus our H value times the area of the outer times that temperature difference right there. So now we can plug in directly to that equation. Now we have our formula for area. And this is going to be off our inner radius. This is going to be off our outer radius right there. So now we have this term right here that we can plug in for in order to solve for this unknown temperature T. So that's what we do on this last page here. We rearrange that relationship there. We solve it just for T right here, and we see we have our heat flux times that area right there, all over our H value here, times our area outer right there, plus our T sub infinity is equal to T. So we can rearrange this a little bit more, and we can see we can simplify this down. Let's just separate this out here like this, and we can see that our 4 pi and our 4 pi cancel, so we're just left with this ratio right here between our inner radius and outer radius squared. So our temperature here for steady state is equal to our heat flux divided by our H value times our inner squared over our outer squared plus our T infinity. Now we can start plugging in our numeric values that we simplified this down. We do that there. We can know our heat flux is given to us as 10 to the 5th in units of watts per meter squared. We have our H value given here as 500 watts per meter squared times Kelvin. So watts per meter squared cancels with watts per meter squared right there, leaving us just the Kelvin right there. Times our, if we take our R value squared there, then we can say our meter squared and meter squared are going to cancel out. We're left with 0.5 over our 0.6 plus our 300K. So we have a K there, a K there. So our temperature is in units of kelvins. Our unit analysis checks out. T is equal to 439 Kelvin for our steady state answer.